So basically, as I said, spintronics basically amalgamates magnetism with electronics because spin comes from the magnetism part, and then this electronics is already existing. Now the two important devices which are basically the most popular spintronic devices, they are spin valves and magnetic tunnel junctions. And I will tell you why these are the most important devices, because these are the devices which has been used in most of the spintronic technology. And now what are spin valves? Spin valves are basically two ferromagnetic layers separated by a non-magnetic spacer layer. Now this non-magnetic spacer layer can be a metallic layer or can be a insulating layer. So if it is a metallic layer, then this structure is called the spin valves. So you see here so forget about this layer for a moment. So let's forget about this layer. So if you see, this is one ferromagnetic layer and this is another ferromagnetic layer, and then there is a spacer layer in between this. Now this spacer can be metallic. If it is metallic, then it is called spin valves. But if this spacer layer is insulating, for example, here you see this yellow one, this is insulating, then this structure is called the magnetic tunnel junctions. And I will tell you why they are called like this in the later part of my talk. And then these are the reed heads which use this concept of giant magnetoresistance. And there is a proposition of spin field effect transistor also. Basically, these are the field effect transistor which are driven by the spin current. And as I already mentioned, the advantages of these spintronic devices are fast switching speed, low power consumption, non-volatility, and it allows you to scale devices in further nanometer dimensions. So now, if you look at the classification of the spintronics is basically broadly classified into three parts. One is this metal spintronics, which has giant magnetoresistance, tunnel magnetoresistance, spin transfer torque, spin Hall effect. These are basically the four salient concepts of this metal spintronics. And then you have a semiconductor spintronics, in which you try to replace silicon by dilute magnetic semiconductors, and then the emerging organic spintronics also. I will not touch these two parts because I am not the right persons to tell about these two things. But given my expertise on this area, I will talk about metal spintronics mostly. So yeah, any question?
Yes, sir. Sir, what we do by changing the spin of the electron, and is there any particular, there's a particular orientation for plus half and minus half spin?
You will get to see this. Just wait for a moment. I will tell you these things. So what basically your question is basically what spin does to your electronic devices, right?
Yes, sir.
Yeah. So I will tell you this part later. Yeah. So
what is spin?
Spin is basically a movement. You have a magnetic movement, right? So if you look at the electron basically, to be precise, it's basically a kind of spin angular momentum. So like electron revolves around its orbit, so it has an orbital angular momentum, right? But it also spins around its axis, and these spins can be up, so clockwise and anti-clockwise orientations. Then for one orientation we call it a spin up electron, and then for other orientation it is called the spin down electron.
So electron can also be waves, no? So where spin can come here?
Electron, what did you say?
Electrons can also be waves, no? So
yeah, but spin. So if you have you read about this Stern-Gerlach experiment?
No, sir. Please say.
So well, I don't know. I mean, so Stern-Gerlach experiment basically demonstrates this spin property of the electron, because in that experiment what they did, well, right now I don't remember completely which which material they use, but they basically use certain materials, and then they found out that, you know, so electron can have two different spin angular momentum configuration. Well, I think if you are interested in this, then maybe I will tell you about this experiment in detail in the next lecture. But why I am bringing this Stern-Gerlach experiment here? Because Stern-Gerlach experiment demonstrates this existence of spin of the electron, that it has the spin property of the electron. So so spin is basically a, you know, spin arises due to the precession of the electron around its axis, and then you will see that how this spin movement basically transfers the spin angular momentum. So it's a movement basically, right? So yeah, so I was here. So I have divided.
So one more question.
Yes.
So in an orbital, there are two electrons, one has plus half and other has minus half spin. So do we change both of them or one of them, the spin?
No, spin, you don't need to change the spin. Spin it's an intrinsic property, right? Spin is basically an intrinsic property of the electron. So like you know this Pauli exclusion principle?
Yes.
Yes, sir.
So Pauli exclusion principle is also associated with this. No two electron can have the same quantum number, right?
Yes, sir.
Right.
So why no two electron cannot have the same quantum number? Because they have a different spin configuration.
Yes, sir.
So it's the same, because it is the same concept basically. That.
So then what we are manipulating, like if you're not changing the spin?
You just wait. I am going into that part. You just wait, because I'm just introducing things, so you will see that how we are using this spin here. So
Okay.
And what are the advantages? You know, it is basically giving in your devices. So I will tell you this, because I have worked on this, so don't worry about that. So I will explain these things. So so I have divided the entire journey of spintronics into 3 parts. And this journey started at late 80s, I would say, because 1988 this giant magnetoresistance effect was discovered, and because of this effect, these two gentlemen were awarded the Nobel Prize in 2007. So if I have basically so these are basically 30 years. If I take 90, then so I have divided this 30 years of spintronics journey into 3 parts. So this is spintronic 1.0, in which I will discuss these giant magnetoresistance and tunnel magnetoresistance effect, and then how these effects have revolutionized our hard disk drives and random access memory. So the simpler concept is the magnetoresistance effect. So this effect was quite old. So this effect was already there in 1970s or something like that. And this effect is very simple effect. What is this effect? So you take any ferromagnetic metal, right? Any ferromagnetic metal like iron, cobalt, nickel, any ferromagnetic metal. And when you place this ferromagnetic metal in the presence of a magnetic field, right? And you send some current there, so you have some resistance, right? Resistance of this ferromagnetic layer. So what is this effect? This effect says the electrical resistance of this ferromagnetic metal changes under the application of the external magnetic field. And how it changes, you see? So here the resistance is this and this. So I have basically plotted here the percentage change in the resistance. So you see that within this range of -20 to 20 oersted. So 1 millitesla equal to 10 oersted basically, right? So you see that how the resistance changes. And this I have I have measured this magnetoresistance for a ferromagnetic layer of nickel iron. Nickel iron is basically a ferromagnetic alloy, which is of 10 nanometer thickness. So for this particular layer, you see this how this electrical resistance changes with magnetic field. So this is called magnetoresistance. Magnetoresistance. Resistance changes with the application under the application of the magnetic field. But the problem here is, you see, if you look at the change in the resistance, it is very small. How much it is? It is even less than 1% change in the resistance. So until that time, you cannot use this effect for your technological applications, because this effect is very small, too small to detect basically, right? Now, why this effect arises? This effect arises because of this electronic orbital configuration. So so this is, well, to be precise, there are many things happening in these materials, because when the electron moves inside the metals, there is a scattering. The scattering can be of the origin of the scattering can be many. The scattering takes place because of the ions also, because of the impurities also. But the simpler picture is, you see, if this orbital, and this is the basically the movement of this electronic orbital. So you see, when the magnetic field is perpendicular to the current, so this is the conduction electron. So current is, so electron goes opposite to the flow of current. So when this conduction electrical current is perpendicular to this magnetic field, the scattering is very less. That's why your resistance is very small. But when this current is parallel to this magnetic field, then the scattering is very high, and then your resistance is very high. So because of this, you obtained this type of magnetoresistance loop. So how did I measure this loop? I started from this very high field, and then I goes to the lower field side. So I got this, I observed this peak, and then it saturates, and then again I came back from negative saturation field to positive saturation, and then I again observed this peak here, and then this is this. So this is how this magnetoresistance response is measured. And you can also see that this magnetoresistance response is also anisotropic. What it means? Anisotropic means it depends on the angle between the current and magnetic field. So I have only shown for two extreme cases, I perpendicular to magnetic field and I parallel to the magnetic field. So I parallel to the magnetic field, the resistance, as I said, that when this is parallel, then this scattering is very high, then the scattering is very high. The resistance also increases for the parallel configuration, and for the perpendicular configuration, the resistance is very small. So this was a very simple effect which was already there. Now what happened in 1988 and the consecutive year of 1989. So these are the two papers which were published during this time, and these two papers are basically the revolutionary papers, because these papers are the basics for the entire revolution which you have witnessed over the last 20 years. And why I'm saying this, because I will tell you this, because so what has happened 1988. So these authors, and these authors were led by Albert Fert, he's here, and these authors were led by Peter Grunberg. So Albert Fert, what they did, so Albert Fert group at France, what they did is they observed, they basically measured the same effect in these multilayers of iron and chromium. So here I have shown only for a ferromagnetic layer. Here they basically fabricated these iron chromium multilayers. So basically you see here 30 angstrom thickness, and here the 18 angstrom thickness, and this is 30. 30 means these are alternate multilayers. So 30 times of this one iron chromium, and then again iron chromium. So these are the successive layers. So this is called the multilayer structures. So what they observed in these multilayer structures, this change in the resistance is very high. Very high means it's, you see, I mean, if you look at this change, so for this particular thickness of 30 angstrom and 18 angstrom, this is the change. But when they reduce the thickness of this chromium layer, which is from 18 angstrom to 12 angstrom, the change gets even more than double. And then if you reduce the thickness further 9 angstrom, you see the change from here to here, it's almost 4 times or 5 times. Right? So what they observed is that for this particular multilayer structure, this resistance change is very high. That's why they call it a giant magnetic resistance. But still it is less than 10%. It is 3 or 4%. It's not very high, but the factor is very high. You see that the resistivity is lowered by almost a factor of 2 in the magnetic field of 2 Tesla. But you should also note here that the field required is very large also, which was not a very good sign, because it's not very convenient to have a very large magnetic field in any devices, because it's not very convenient. And
Sir,
then yes.
Sir, here we are talking about the resistance of the material. So
Yes,
that is the we measure it by the current passage.
Yes,
right?
Yes, correct.
So the magnetic field, it is applied on these electrons here. Yeah. And the randomness increases, you are saying.
See, so if you are asking about how this experiment was done, so this experiment was done, let me open my video, I think, because I'm explaining. Where is this? So you can see me now, right?
Yes, sir.
Yeah, so if you're asking about how this experiment is done, so you have a layer. So let's say this is your layer, right? So what you do here, this is your, so it's basically a nanometer film, but let's take it, this is nanometer size film, let's say. So what you do here, so you make contacts here in this layer. So you make one contact here, another contact here, so you make 4 contacts. And these 4 contacts are in the 4, so we call it a 4 probe geometry. So you make 4 contacts, and then you apply, so in one case you apply the magnetic field in plane, right?
Yes, sir.
In plane, and then so you supply current to 2 terminals, and then you measure the voltage to another 2 terminals. So this voltage divided by I gives you the resistance, and that resistance, if you measure this resistance as a function of magnetic field, as a function of changing magnetic field, then you observe this type of response. And to be precise, the response is basically this type of. So this is the response which I have measured in our during my PhD. So you observe this type of response, and this let me also tell you, this peak width also tells you about the coercivity of the material. I think you already heard this word coercivity, right? Every ferromagnetic material has a coercivity. So this width of this response basically gives you the idea about the coercivity of the magnetic material. So this is how you measure this, and then you in other configuration you apply the magnetic field perpendicular to the current, because your current is always in plane. So you apply the magnetic field perpendicular to this, or you can do it in this way also. Like your current is here, then you can apply the magnetic field here also in plane. So then your current and magnetic fields are perpendicular.
Yes, sir.
Yeah, and the other thing, do you know about Hall effect?
Yes, sir.
So this experiment is quite similar to Hall effect. In Hall effect, the only difference between this experiment and this Hall effect is, in Hall effect, current, voltage, and magnetic field all are perpendicular to each other. So you take any metal and semiconductor, and then your current, magnetic field, and the Hall voltage which is developed, they are all perpendicular to each other. Here the difference is everything is in the in plane. So you apply the current, your magnetic field is perpendicular to the current, and then you measure the voltage.
Sir, I have a doubt here. Sir, magnetic field does no work on the electrons, right?
No, magnetic field try to orient these. That's why this effect is only observed in the ferromagnetic materials. Why? Because ferromagnetic materials have spins, So what magnetic field does? Magnetic field try to orient all the ferromagnetic movements, individual movements of the ferromagnetic material. They get aligned along the direction of the magnetic field. So that's the use of the magnetic field. Here you can see in this picture, you know, when you apply this magnetic field, all these individual movements. So these are basically the individual movements. They try to align along the direction of the applied magnetic field.
Right. So here it is doing some work.
Well, this process is so fast actually, you know, this process is very fast. So magnetic field is magnetic field is so strong that it basically, you know, it aligns the movements very fast to this orientation of the magnetic field. So right, and then so yeah, I was telling about this. So in the consecutive year, Grunberg group also observed the similar effect, but they observed this effect in iron chromium superlattice structures. So their if you look at their structures are slightly different. So their structures here, they use only iron and chromium, and they use iron, chromium, and iron. So basically, this is basically typically a example of a spin valve structure, because two ferromagnetic layers are sandwiched between this chromium layer. So chromium is basically the, you know, spacer layer, and their observation was, so they observe a very giant change in the magnetoresistance again. So and they compared it with this iron 25 nanometer thickness layer. So in a 25 nanometer layer of iron, they observed this much of magnetoresistance response. But when they compare this with this structure, so you can see, you know, look at this difference between this response. So about, you know, it's more than it's about double, and both group has attributed this effect to the spin dependent scattering of the electron. So basically they claim that, you know, the ferromagnetic layers, ferromagnetic layers. So I have shown here, every ferromagnetic layer has a different density of states at the Fermi level. So, you know, this is s orbital, this is d orbital. So if you look at this density of states at the Fermi level, so for a spin up electron, they have a different density of states, and for a spin down electrons, they have a different density of states. And I would also like to mention here is that the critical electrons which take part in this spintronic devices, they are the d electrons. Mostly they are the d electrons, because they are the outermost shell electrons of these iron, chromium, iron, nickel, and cobalt. So that's why we use always the density of states of these d electrons. So they are the different density of states for spin up and spin down electrons. And because of this density of electrons, the scattering for different spin configurations is different. And because of this, they observe this large magnetoresistance response in these structures. So this was a very important discovery, because I will tell you in the following slides that how this discovery has drawn a lot of attention to the researchers. And you see here that so they were, and this is the reason why they were awarded the Nobel Prize, because what happened after their discovery? Look at this evolution. So giant magnetoresistance was discovered in 1988 and 1989 also. And then first GMR hard drive read head was invented by IBM in 1997. And then this tunnel magnetoresistance, which I will explain in the next slide, this tunnel magnetoresistance effect was observed, and this effect was quite motivated by this discovery, by the way. And this TMR magnetoresistance was observed in 1995, and then first TMR hard drive read head was launched by Seagate in 2004. And then magnetosystem random access memory was launched by Freescale in 2006. And because of this revolution in this data storage industry, they were awarded the Nobel Prize, because they were the one who started this journey and motivated the next generation of researchers. And you see what you are witnessing, you know, the entire change because of this discovery. So so this is basically a cartoon to just show you that how this spin up electrons can easily transmit through this channel. If the alignment of the one ferromagnetic layer and another ferromagnetic layer is parallel to each other, so this electron which is anti-parallel to this can easily scatter, but the electron which has the same orientation with this layer, it experiences a scattering, or it experiences a large resistance, and because of this spin dependent scattering of the electron, this response was very high. And you see here in other configuration, if the antiparallel spins goes, if this spin down spin goes through this alignment of spin, it can easily scatter, but when it sees the same orientation as it has, then it scatters. So because of this different spin dependent scattering through this channel, the magnetoresistance response was very large, because the scattering also gets very large. Now I am emphasizing so much on this magnetoresistance part, and why I am emphasizing on this magnetoresistance part. Why this magnetoresistance is so important? Because you see, this magnetoresistance response is basically it basically gives you a sensing capability. You know, so if your magnetoresistance response is very high, it means that you have two states: high resistance state and low resistance state. And larger the magnetoresistive response, better will be the sensing capability. And what happened because of this, that if you have a very large magnetoresistance in a thin film, then if you try to reduce this size of the thin film, your magnetoresistance still remains intact. So for example, let's take with this, like I have observed this magnetoresistance of 0.3% in this layer. Now if I try to reduce the size of this film, let's say the size of the film is, let's say 100 micrometer by 100 micrometer. Now if I try to reduce this size of this film by 50 micrometer by 50 micrometer, and then I try to measure this magnetoresistive response, it will be even less. But if your magnetoresistance response is already very high, then it allows you to make very high quality sensors at a nanoscale. And this is exactly what happened in this last 10-20 years. Because what happened after this discovery, this effect came into picture in 1995, and this effect was proposed by Indian scientist whose name is Jagdish Mudera. He's currently a professor at MIT. So I think he was a postdoc at that time at MIT, or yeah, he was a postdoc at that time. And what he observed is that he basically fabricated magnetic tunnel junctions. And why I'm calling it magnetic tunnel junctions? Because if you look at this spacer layer here, which is aluminum oxide, this is an insulating layer. So whenever this spacer layer is insulating, it is called magnetic tunnel junctions, because then this effect arises due to the tunneling of the electrons. So here you see it has a different density of states. So when you apply certain bias voltage, this is the bias voltage, then it has a different density of states. It has a different density of states, and because of this different density of states of these electrons, the electrons, one type of electron which are spin up or spin electron, they experiences a different tunneling, and the other type of electron experiences a different tunneling. And then you have this tunnel magnetoresistance tunnel magnetoresistance ratio calculated R antiparallel minus R parallel divided by whichever is higher or whichever is lower. So he observed a change of about 11.8% in this structure, in this tunnel junction. So you see this change is about 11%, which is significantly higher than the giant magnetoresistance. So this was the turning point. This was also the turning point, but their discovery or their experiments were quite motivated by this discovery of the giant magnetoresistance, because they thought that if they can observe a large magnetoresistance change in this structure, why can't we why can't we measure such structures? So, and they did it, and they observed a very large change in the magnetic resistance. And then this was the turning point, and then you see the growth. So at 1995, this change is the magnetic resistance was observed about 12%, and then this was linearly increasing up to 2000 and 2002, and then you see that when this barrier was replaced by magnesium oxide barrier, this spacer layer was replaced by magnesium oxide barrier, there is a abrupt change in the magnetic resistance response. And then in 2004 or in 2004 or 2008, Tokyo University has proposed a magnetic resistance change of 604%. So now you have a very and if the change in the magnetic resistance is so large, then your sensing capability or sensing quality is also very fine, or very fine at the nanoscale. And this is the reason why you have a very high quality sensor at the nanoscale, which can read the information and which can write the information also. We also tried to fabricate these magnetic tunnel junctions during my PhD, and we used this type of structures, but we were reasonably successful in obtaining the very high magnetic resistance. Our magnetic resistance was not very high at that time, but yeah, we tried to fabricate these magnetic tunnels. So this is basically a junction. So this is a bottom ferromagnetic electrode, and this is the top ferromagnetic electrode, and in between there is a magnesium oxide layer, and then this intersection point is called the junction. So this junction is of basically so this is the barrier size, and this junction is about in nanometer size, in nanometer area. And then you have this and look at the sensing capabilities. They have a very fine sensing quality because of this large magnetic resistance change, even at the nanoscale. So this is a very beautiful plot which shows the progress in the last 10 or 20 years. And you see this tremendous growth of magnetic resistance response after 2004. And this is why you see the trend, how trend changes in the last 10 years. You have your hard disk storage capacity is of in terabyte. And I will show you now this Evergreen or some company, Everspin. Yeah, Everspin has launched a hard disk drive of storage of 20 terabyte last year. So this growth was possible because of this. So now the question is how this information is stored in these spintronic devices. Well, the concept is very simple. That now you see here there are two ferromagnetic layers separated by a spacer layer. It can be a spin valve or it can be a magnetic tunnel junctions. So what happens? The change in the resistance, as I mentioned, it depends on the relative orientation of the top and bottom ferromagnetic layer. So if the alignment of the spins is anti-parallel, then it will give you a very high resistance state, and if this is parallel, then it will give you a low resistance state. So this is exactly what I have shown here. So this anti-parallel state, which is basically a high resistance state, is called the 1 state. And this parallel state, which is basically a low resistance state, this state is called the 0 state. And you know that every information is read in terms of these digital configuration 100, 1001, and this. So these are basically these bits. So these resistance state provides you these bits configurations. So better is the sensing capability, better is your reading capability also. And then now the question is how these states are achieved. So you see, if you don't have any magnetic field, then you have this anti-parallel orientation of the magnetization of the top and bottom ferromagnetic layer, and it can be parallel also. But once you apply it, so here you can see that how these states were achieved. Now this green layer, which I will discuss in the next slide, this green layer is basically the antiferromagnetic layer. And what is the use of this layer? This layer basically, what this layer does, this layer basically holds the ferromagnetic layer magnetization of the bottom layer. Because if you have a two ferromagnetic layer, and both ferromantic layer has, parallel, let's say parallel alignment, and if you apply the magnetic field, then both, for example, if you are applying the magnetic field in the opposite direction, both ferromantic layers will flip. Then how do you achieve the antiparallel state? So in order to achieve this antiparallel state, it is very essential to lock the magnetization of one of these two ferromantic layers. So you can lock the magnetization of the upper ferromantic layer, or you can lock the magnetization of the bottom ferromantic layer. So this green layer, which is basically antiferromantic layer, it basically locks the magnetization of the bottom ferromantic layer. So you see that in both the configuration, the magnetization layer is fixed. That's why it is called a fixed layer, and this is called the free layer, because the magnetization can change in the top layer. And now what happens? So when you try to measure the magnetic response of this structure, so here if you apply a very large magnetic field, then it can saturate. So both have the parallel orientation. But when you try to reduce the magnetic field, one of the ferromantic layer flips. And which one will flip? The top one will flip, because it is very easy to flip the magnetization of this layer. So then one of the ferromantic layers flips, and then it has an antiparallel state here. And then if you further try to increase the magnetic field in the negative direction, then the other ferromantic layer magnetization will also try to flip at a large magnetic field. And then you have this parallel state again. And then when you reverse back in the positive field direction, then again there will be a point when the top ferromantic layer magnetization will flip, and then you will have this antiparallel state, and then you will have again this parallel state. Now corresponding to this antiparallel state, you see a large change in the magnetoresistance. This change in the resistance. So corresponding to this antiparallel state, the change in the resistance is very high, and that's why. So this is one state and this is zero state, right? So this is how these states were achieved, and this is how the information is stored in terms of this one state and zero state. So this effect, which basically locks the magnetization of one of these ferromantic layer magnetization, is called the exchange bias effect. It's called the exchange bias effect. So, okay, where is this slide? Yeah, so let's go. I think so this let me just briefly explain you how this effect basically locks the magnetization. So this effect is basically this exchange bias effect. So what is exchange bias effect? You have a ferromagnetic layer, and if you try to record the magnetic response of this layer, then you have this hysteresis behavior, which you have already studied in your 10+2. And then if you try to grow this ferromagnetic layer over an antiferromagnetic layer, then due to the exchange interaction of the spins of the antiferro and ferromagnetic layer, there will be a shift in the hysteresis loop, and there will be a broadening in the hysteresis loop also. You see that there are two effects here. One, this hysteresis loop shifts in the opposite direction of the applied magnetic field, and the second effect is it basically broadens the hysteresis behavior. So this effect is called the exchange bias effect. And why this effect arises? So this is basically an intuitive picture of this effect. So here you can see these are the antiferromagnetic or antiferromagnetic spins, and these are the ferromagnetic spins, and this structure is basically heated to a temperature which is greater than the Néel temperature of the ferromagnetic material. Then these spins, so antiferromagnetic material gets paramagnetic if it gets heated beyond the Néel temperature of the antiferromagnetic material. Now from this temperature, if it is cooled at a magnetic field of HCF, then antiferromagnetic spins try to follow the magnetic field. So then it basically forms a ordered structure, like one sublattice of spin, another anti-sublattice of spin, and then another sublattice of spin. Now, because of this ordering of spins, there is an exchange interaction across the interface. And because this exchange interaction basically what this exchange interaction does, it holds the nearest spin at the interface, nearest ferromagnetic spins at the interface. So when you try to reverse the the magnetization of this layer, these spins will hold these spins. Then you will require a very large magnetic field to flip this magnetization, to flip these ferromagnetic spins. So your magnetization reversal will take place at a very high magnetic field. Now on the way back, when you try to reverse these spins, then since they are already holding these spins, or they have a tendency to basically hold these spins, then this second magnetization reversal will take place at a smaller magnetic field compared to this one. So the overall effect is basically you have a shift in the hysteresis loop because of this locking, because of this exchange interaction of the spins across the interface. Now, if this anisotropy is very weak, so this I have assumed for the case of strong and antiferrometric anisotropy. So strong antiferrometric anisotropy means the tendency of the spin to remain fixed at their sublattices, and in some cases this anisotropy can be weak. Then if the anisotropy is very weak, then you only observe this increase in the coercivity, because then it basically try to, so the ferrometric spins will try to drag these spins during the first magnetization reversal. So this effect, so this is the effect which is exchange bias effect, which is exploited in this data storage industry in order to lock the magnetization of one of the two ferrometric layers. I explained this effect because my PhD work was also in this was also involved in these exchange bias studies of different ferrometric and antiferrometric layers. So I will not go into that part, but yeah, so here I was explaining to you so how this configuration is achieved. And then so I just took these pictures just to just to show you the tremendous progress in the last 30 years. So we have this computer in 1956, which is so much bulky. So they are, these people are, they are basically shipping this computer from one place to another place. So you see these photos, these are the real photos. And if you look at the capacity of these, it's very less. And they are very slow also, 50 disk, 100 sites, 100 tracks per site, and the writing speed 8 kilobyte per second. So you see, and the cost is 30 to 100 US dollar. I think this is per month. I think maybe it is renting rate or something like that. So this was the computer we had in 1956, and then some improvement did take place in 1973, and then we have this storage of 70 megabyte, and the speed also increases, but still it is so bulky, as you can see in this picture. And these are the read heads. Look at these read heads. So they are also so bulky at that time. And then you see this picture after 90. Look at this slope of this curve. It was very very monotonic, but then you see here it is very abrupt because of this discovery. And then again, I have already mentioned these things. So up to 2010, we have already these GMR heads and TMR heads, and then we are talking about this perpendicular recording using this concept of perpendicular magnetic anisotropy. So so this I was explaining to you, this exchange bias effect, and so these are the things which we have done during my PhD. So we have observed this effect in this structure. So here we have this iridium manganese alloy, which is an antiferrometric material, and this nickel iron is basically a ferromagnetic material. So we fabricated this 15 nanometer thickness of antiferromagnetic material, and then 10 nanometer thickness of ferromagnetic material. And then we measured this hysteresis behavior at low temperature, 10 Kelvin. So you see this very large exchange bias field of 270 oersted. And then when we try to repeat this experiment, we observed a reduction in this exchange bias, which is also a very peculiar characteristics of these exchange bias systems, which I will not go into detail because it is not that easy to understand these things. But I'm just trying to show you that how these things are actually measured. And we can also see this effect in terms of this magnetoresistance response. So you see this, for this exchange bias system, these two peaks are not symmetric. Otherwise, if you record this magnetoresistance response for any ferromagnetic layer, they are very symmetric. This is not symmetric because of this exchange bias effect. Because you see here when I record this hysteresis behavior, this reversal mechanism during the field decreasing branch and during the field increasing branch is different. And this difference in this reversal mechanism is reflected here in this magnetoresistance response. So this is called basically a asymmetric magnetization reversal. And this is a peculiar characteristics of exchange bias systems. So that's why this is basically asymmetric. And then I record this consecutive magnetoresistive response. This symmetry gets reduced. This asymmetry gets reduced. And then you measure the consecutive magnetoresistive response. Then this asymmetry gets removed. Because of this cycling of this measurements, and this happens because of this unstable spin configuration at the interface. This asymmetry gets this asymmetry goes away because of this instability of the spins at the interface. Because when you repeat the measurements, this instability gets reduced, so your spins gets more stable at the interface, and then they basically translates into this symmetric magnetoresistive response. So this is the effect. This is the experiment which I have done during my PhD, and then we recorded this behavior, and then we did some analysis which I will not go into detail. And so these are the hard disk milestones in the last 30 years. So you see this giant magnetoresistance effect discovered. First hard drive was launched with GMR readout in 1997. 2005, first hard drive at 500 GB was launched by Hitachi, and then first hard drive with TMR readout was launched by Seagate. First hard drive with perpendicular magnetic anisotropy was launched in 2005. First hard drive at 1 terabyte in 2007, and 2009 first hard drive at 2 terabyte. And then if you see here in 2020, first hard drive of 20 terabyte was launched by Western Digital. I was wrong, actually. I was saying Everspin, but it was Western Digital. So Western Digital has launched. So this was possible because of this large magnetoresistive response. Yeah, this was the photo of this hard disk drive. So this is where we stand right now. And this was launched. This was already launched, magnetic random access memory, and this random access memory is basically the non-volatile random access memory. But the problem is you don't see this in the market because there are some issues with the commercialization of this magnetic random access memory. So in order to commercialize such devices, you need to deal with several things like cost, durability, these things. So there are some issues still, but it was already launched in 2006 by Freescale. And this is completely non-volatile memory. So there are other works also going on in parallel to this type of memory, which is magnetoresistive memory. So there is SRAM also, solid random access memory, and flash memory concept is also there. But as of now, MRAM has an upper edge with respect to other available options. But there are few issues with the commercializations, and as of now, the future looks quite good of these random access memory. And then I think, how much time do we have now?
I think we already crossed time, but since we don't have any extra class, we did not mind waiting.
So can I continue for a few minutes, or?
Yes, you can continue.
Yeah. So this is the part which involves this tunnel magnetoresistance and giant magnetoresistance. But the significant contributions to this revolution was due to this large tunnel magnetoresistance. And this tunnel magnetoresistance, why it is called tunnel magnetoresistance? Because it occurs due to the tunneling of the electrons through a spacer layer, which is basically an insulating layer. And this tunneling is the effect is quite similar to giant magnetoresistance, here also one type of spins, they experiences a large scattering while tunneling through this spacer layer, and the another spin configuration experiences a less resistance to the tunneling of the electrons. So one spins can tunnel very easily through this structure, and another spins cannot tunnel very easily through this structure. And this is just a concept how these elements are used in order to read these information. So here you see that one such an element is used, and this is but this is more like an engineering concept, but this is basically the idea is basically how it basically provides you this different configuration for this 1 state and 0 state. So this is how this is used, and then this is the photograph for one particular bit. Otherwise, the image is, if you look at this, the actual image looks like this. So there are different bits here. So 1 0 1 so this is also, and these are these bit lines. So this is how they basically this information is read through these tunnel. Yeah.
Actually, I have a doubt here. If the magnetic moment in ferromagnetic layer is anti-parallel, then we called it 1, and when it is parallel, then 0. Then yes. How quantum computer arrived here that you are using qubits, 3 bits?
See, I cannot give you the answer to this question because I have not very good knowledge about how these things are used in the quantum computer, because that is not my expertise. I can my expertise is in this even my expertise is not in this tunnel magnetic resistance thing. But yeah, because since I have used this exchange bias effect, then so that's why I know about these things. But I have not so far I have not explained to you what is my expertise in this field. So the spintronic 3.0 is related to my expertise. So I worked with these oscillators. I used these spin based based current. I will explain you what is spin current. So I use this spin based current to drive nanoscale oscillators, which are basically spintronic oscillators, you can say. So yeah, so your question, sorry, I mean, I cannot answer this question because I don't know. I frankly don't know. Because as far what I can say that these I don't to my best understanding, these junctions are not yet used for the quantum computing. So these junctions are only used for sensors. So you see, if you see any sensors at the nanoscale, then you can definitely question that whether they are GMR sensor or TMR sensor, because their original objective is to provide the sensing capability at the nanoscale, because you have no option otherwise. So these are basically a very high quality magnetic field sensor which are used at the nanoscale. Yeah. So yeah, and then yeah, here I was. So now here starts my area of research. So this is basically spintronics 2.0, and these two gentlemen, well, I would say they deserved the Nobel Prize because they have also started a new journey or new breakthrough in this area of spintronics. And one of the gentlemen died in 2019. Slonchowski is no more now, but Berger is still alive. So what they discovered, so they basically, they discovered theoretically this concept of spin transfer torque, which basically combines with the magnetic tunnel junctions to give you a STT MRAM. So the current latest random access memory is basically the spin transfer torque effect based random access memory. So basically researchers combined the magnetic tunnel junctions with the spin transfer torque. And what this spin transfer torque does, this spin transfer torque basically gives you the the ability or gives you the capability to drive these devices with a very less energy. And I will tell you how it is possible, how it was possible. So now I am introducing a very different concept, and I think you are not aware of this concept. So you see, electron has, as I mentioned, the electron has a charge as well as this spin. So which is basically associated with this angular momentum. Now you know about this current, which is basically electrical current. So charge with the flow of charge gives you this charge current, and this was, you know, quite a very old concept. And then because of these spins of the electron, you can have a spin current, but you can only have this spin current under certain situations. And I will tell you what are these situations. So spin can also offer you a kind of current which is called spin current, a concept that attracted much attention in the recent years. So what is this spin current now? So you see here, sorry, what did I do? Can you see my screen?
Yes, sir. Yes, sir.
Yeah. So you see, this is unpolarized current, means this is charge current. When I say unpolarized current, unpolarized means it is unpolarized with respect to spins. So unpolarized current has zero charge current, zero spin current, but it has a non-zero charge current. So it is basically a charge current basically. Now, by some method, and I will tell you what are those methods. By certain methods, if you can change the balance of these spins. For example, you have more spin up electrons or less spin down electrons, or vice versa. You can have more spin down electrons or less spin up electrons. So basically, if you can create this imbalance of these two spins, then you will have non-zero charge current and non-zero spin current. Because then you have, if you look at this net flow of the spins, so you will see from a particular frame of reference, you have more spin up electrons are flowing. That's why this charge current also associates a spin polarized current. So this is basically a spin polarized current. So spin polarized current is basically a current in which there is an imbalance of the spins of spin up electrons and spin down electrons. And if you can, by a certain method, if you can create a imbalance in such a way that spin up electrons are moving exactly opposite to the spin down electrons. So basically spin up electrons are moving in this direction or spin down electrons in this direction, then you have no charge current. Then you have no charge current. You have only spin current, and that's why this spin current is called the pure spin current. So pure spin current means you have 100% spin polarization of electrons. So you can, pure spin current means you have spin up electrons flowing in a one particular direction and spin down electrons flowing in another particular direction, and they are exactly opposite to each other. So I will first, so charge current you already know. All your modern electronic devices are based on this charge current. Sorry. So what happened? So charge current you already know. I will explain you the consequences of this spin polarized current and pure spin current. So I will start with this spin polarized current. So how do we generate this spin polarized current first? So so charge is basically conserved, spin is not conserved. So first you have to you have to see what happens. This is basically a magnetization dynamics of spins. So you have a ferromagnetic layer here, right? And this ferromagnetic layer is subjected to an external magnetic field. What happens? The individual movements of this ferromagnetic layer, it starts to precess around this external magnetic field. Now I have shown here a vector here. And why I have shown a vector here? Because this precession of the individual movements, it starts collectively. So collectively it will, you will see it as a vector, magnetization vector. So the whole movements basically, starts to precess around the magnetic field. So you will see a vector is basically precessing around this external magnetic field. But what happened due to this intrinsic property of these materials? So there is a damping offered by these ferromantic materials, and due to this damping, this precessional motion gets damped very fast. And you see that after a certain time, this magnetization vector aligns along the direction of the external magnetic field. So these two gentlemen, they basically proposed an idea. So they proposed that if by some means, if you try to overcome on this damping effect, then you can have a steady state precession of this magnetization around this external magnetic field, and that this precession gives you basically microwave signal, because the precession is so fast, it can generate a frequency of gigahertz even. You will see that. You will see this part in the following slides. So theoretical description was given by this Landau-Lipschitz equation. So in Landau-Lipschitz equation, so this is basically the same theoretical description of this dynamics. So according to Landau and Lipschitz, so this magnetization dynamics can be represented by an equation in which you have a precessional term. You have this precessional term which is precessing around this external magnetic field, and then this damping term which arises due to the intrinsic property of the material, and this damping can be different for different ferromagnetic materials. So due to this damping torque, this precessional motion gets damped very fast. Now, if by some means, if you can introduce an additional spin transfer torque to this magnetization dynamics, so you can have a steady state magnetization precession. So this, you see, this green one is exactly opposite to this damping torque. So what it does is basically it overcomes this, this damping effect, and then you have this steady state magnetization precession. So experimentally, how did we do this? So experimentally, what we do, so we have these unpolarized electrons from a copper material. Copper is basically a metal. So in unpolarized electrons, you have spin up electrons and spin down electrons. So when these unpolarized electrons, so it forms basically a charge current. And then when this unpolarized electron passes through a ferromagnetic material, which is nickel iron here, and it has a magnetization, oriented along this particular direction, then they basically make these spin polarized electrons, they make these unpolarized electrons spin polarized. So you see here that there is a particular orientation of the spin which follows the magnetization of this ferromagnetic layer. So whenever a unpolarized current passes through a ferromagnetic material, it gets spin polarized. Now it's up to you how you use this spin polarized current. So now how we use this spin polarized current, if we pass this spin polarized current to another ferromagnetic layer which has a changing magnetization behavior. So this is basically a free layer. So when you pass this spin polarized current through this cobalt layer, then what these spin polarized electrons does, it basically exerts a torque to these magnetizations. So it basically does the same thing which I have shown in the previous slide, that it basically provides an anti-damping torque to these magnetizations. And this spin polarized electrons basically drives the magnetization dynamics in this ferromagnetic layer. And when it drives the ferromagnetic dynamics in this ferromagnetic layer, then you will observe the microwave signal. And this is exactly what we have observed here. So we fabricated these nano contact based junctions. Now you will ask me, why did I fabricate this nano contact? Because in order to drive this whole area, you need a large current actually, because in order to generate a reasonable spin polarized current, you need to inject a large charge current. So what we do here is we fabricate this devices into nano contacts. So we basically reduce the area, then the current density at this area is very high. So although our current is very small, but the current density is very high. So since the current density is very high, this current density is sufficient to excite magnetization dynamics at this nano contacts. So these are the nano contacts which we have fabricated. These are actually the scanning electron micrograph image of these nano contacts. So these are 2 nano contacts separated by a certain distance, and this is the scale of 100 nanometer. So these nano contacts are separated by I think 150 nanometer. And then this is how we measure these signal here. So these are the electrical pads which we fabricate. So this is ground, signal ground. So we inject current from here and then measure the voltage also from the same terminal. So this is typically the structure you see here. And then you have, ferromagnetic layer, spacer layer, ferromagnetic layer, and then these are some. So this is basically the exchange bias layer. Here we have used platinum manganese as an antiferromagnetic layer. So these 3 layers basically provides you the magnetic stability to this device. And then when we measure the microwave signal of this device, with this steady state precision, then we observe a microwave signal of about 10 to 30 gigahertz at a current of, you see, if you look at this current is hardly less than 6 milliampere. So this is how this spin polarized current is used to excite or to generate such a high frequency or high quality microwave signal at nanoscale. That's why these devices are called oscillators, because what we do here, we inject DC signal and we extract AC signal. So we extract this AC signal at a certain frequency, which frequency is given by this. So these are called basically the spin transfer torque nano oscillators, because these oscillators are very small. You see, if the dimension of this nano contact is about 100 to 150 nanometer. So this is here, you see this 150 nanometer. So in 150 nanometer device can give you a microwave signal of 30 gigahertz, which was quite remarkable. So so we observed this effect. So here in 2018, so this is the paper we have published. So in 2018, we basically demonstrated this high frequency microwave signal in these magnetic tunnel junctions. These are basically nano contact magnetic tunnel junctions. So you see, why I was showing this this slide to you, because you see here the magnetoresistance is 36%. So this is the magnetoresistance which was measured on these nano contacts. If I measure the magnetoresistive response of this entire stack or entire layer stack, it's very high. It's about 200%. So basically, the point which I'm trying to make here is that if you try to reduce the dimension, your magnetoresistive response also gets lowered. So your sensing capability also gets lowered. So you need a very large magnetoresistive response in order to make a very high quality sensors at the nanoscale. So since these stacks provides us a very good magnetoresistive response even in this layer stack, we were able to obtain a very reasonable amount of magnetoresistive response at this 150 nanometer dimensions. And because of this large magnetoresistive response, we have a large signal also here. So these signals, this is the signal. This is the power of the signal. These color maps gives you the idea about the power of the signal. So that's why. So these are basically the magnetic junction based oscillator, and these oscillators are used for many purposes. And I think I will stop at this point. So I will extend this part to my next lecture, and then I will tell you that what are the possibilities and where we are heading towards, and what is the future with these devices, with these oscillators. So just to motivate you at this point, that these oscillators are used, can be used for your next generation spin wave computing also, where you try to compute things with the help of spin waves. So like right now you use this. So quantum computing is also one branch, but there is another branch which is called magnonics. So magnonics is basically we use the quanta of these spin waves, which are called magnons. So you have a photons, which are the quanta of electromagnetic waves. Similarly, you can have the quanta of these spin waves also. And these spin waves quanta are called the magnons. So you can use these magnons in place of electrons to compute the, yes.
Actually, we have intro of finance club now.
Yeah. I sorry. I just asked you whether I can continue now, but I should stop here. Thank you. Thank you for your patience. So let's stop then. Right. So okay. So we can leave then, right?
Sir, just one request. Like whatever slides which you had shown just now, can you share those? Like, even we would like to read them later once more.
Okay, so let me just work it out on the slides more, and then I will send it to you then. Right?
Yes, sounds awesome. Cool.
Yeah, but I don't think that you can you will, because I have not written much in these slides, so I don't know how they are useful to you. But if you want, then I can send it to you.
Yes, sir.
All right.
Please.
Yeah. So so I will continue from this from this part to the next in my next, right? Okay, then bye bye.
Thank you, sir.
Bye, sir.
Thank you, sir.
Bye, sir.
Thank you, sir.